Good afternoon, folks. This is your video for Learning Target 13, deriving a rate law from initial rates of reaction. So at the end of this video, hopefully you will be able to use experimental initial rates in order to derive what we call a rate law. And we'll learn what a rate law means in the process. So let's talk first about what we know about the initial rate. In Learning Target 12, we learned that the initial rate law is the rate of reaction, or how fast reactants are turning into products at the very instant the reaction starts, at time equals 0. We found this using cheap and easy calculus, meaning we drew a tangent line, tangent to the graph of a concentration versus time graph at time 0. So you'll notice, you might recognize this line here. We drew this tangent line at point 0, 0, found another point, found the slope of that line, and we called the slope of that line the initial rate of reaction at t equals 0. Now notice here, this isn't a concentration versus time graph. This is a volume versus time graph because we can get the rate of reaction if we're creating a gas by measuring the volume of that gas. So why does this happen to work here? So I'm going to show you again this collision simulation to remind you what effect concentration has on the rate of a chemical reaction. Okay, so you've seen a simulation in Learning Target number 11. I've got here some blue particles and red particles, and we know a reaction will occur when those particles collide with each other with correct orientation, correct velocity, and enough of those collisions occur that you get enough measurable products. So we've got this collision here, collision counter here, and I'm going to do this sample for 10 seconds. And we get 115 collisions in 10 seconds here. Now, if I decide to increase the concentration of any of the reactants, we measure it again for a 10-second period. We've dramatically increased the number of collisions that have occurred and thereby increased the amount of products that we can form. And so this is why concentration directly dictates the rate of a chemical reaction. So let's define what we mean by rate law. So rate law is defined as an equation to illustrate the rate of a reaction. So let's take this generic chemical reaction here, where you've got reactant A, reactant B with particular stoichiometric ratios of X to Y that will make product C and product D with particular stoichiometric coefficients. Here's what a rate law would look like in one particular version. So notice here that the rate is going to be dependent upon the concentration of each one of the reactants in a given amount of time. And notice here that those stoichiometric coefficients are put into fraction form. And I'm going to explain what this means in a moment. So the rate at which this reaction will proceed is going to be a ratio of the fraction of the X coefficient times concentration of one of the reactants over time, which is going to be the exact same thing for the second reactant here. And it's going to be equal and opposite to the formation of these products in terms of the concentration of the products in their stoichiometric coefficients. So this seems pretty broad and pretty vague, but when I put it in use with an example that involves a real reaction, it makes a lot more sense. We're going to call this equation number 1, because I'm going to introduce 3 equations in this video, and I'm going to title them with numbers so we don't get a little bit confused. So we can use equation 1 to show the proportionality of how the reactants and products interact with each other and how the concentration of the reactants decrease and the concentration of the products increase. So considering this real reaction where I've got 2 moles of dinitrogen pentoxide to make 4 moles of nitrous oxide and 1 mole of oxygen, if I was to put this in the equation 1 rate law, it would look like this. And all of this is saying is what I have written here. Since I know that for every 1 mole of oxygen that I will create 4 moles of nitrous oxide, the rate at which oxygen is going to be created, it's going to be created at 1/4 the rate of the nitrous oxide, and also be created at half the rate at which the nitrogen pentoxide is depleted. So for every rate at which the oxygen is created, it's created at 1/4 the rate of the nitrous oxide and at 1/2 the rate as the nitrogen pentoxide is depleted. And you might want to pause the video here and take a couple notes at that. And just think about this, talks about the proportionality of the reactants to the products. It does not address the actual rate itself. So this is why this is an equation that isn't as useful as equation number 2, which I'm going to show you next. All right, so let's look at equation number 2, which is going to make a little bit more sense. So same equation, same general form of the equation here, where I've got A plus B is going to make C plus D, and X, Y, P, Q are going to be your stoichiometric coefficients. We can derive this following rate law equation, and this is going to tell us the actual speed at which the reaction proceeds. We're going to say that the rate of reaction is equal to a proportionality constant. K is this proportionality constant, which helps us dictate the rate of reaction, times the concentration of reactant A to the mth power and the concentration of B to the nth power. Now, this is really important. M and N are not coefficients in a chemical reaction. M and M will never appear in your balanced chemical equation. M and N are called what we call orders of the reactants. And orders of the reactants have to be found experimentally, which we'll get to in just a moment here. It is possible that when you're doing some practice problems here, that M and N are going to have the same values as your coefficients. That's just a coincidence. It has nothing to do with what M and M have been found to be using calculations. Orders of reactions must be found experimentally, and I'm going to show you how to do that next. So here's some more information on orders of reactants. We're going to derive this rate law here together in a moment. Just trust me right now that the rate law for this particular reaction can take on the form of K times the concentration of N2O5 to the first power. We are going to say if the exponent is 1, this is a reaction of the order 1. This is a first order reaction. And what that tells us that if the concentration of N2O5 is doubled, the rate at which this reaction will proceed will also double. That's what it means to be first order. If I double the concentration, I will directly double the rate of reaction. It's like an exponential function. Another thing about order of reactants, let's look at that generic equation again. I got this generic equation has this particular rate law. M and M are not X and Y in any way, shape, or form. If I want the overall order of reaction here, what I do is I just add up m plus n. So m plus n is going to be the overall reaction order here. So if m was 1 and n was 1, the overall reaction order is 2. We call that equation number 3. And equation number 3 here is just to tell you how we add up those exponents to get the overall order of reaction. Okay, so let's get to calculating these orders of reactants. As I previously said, orders of reactants must be calculated experimentally in using that initial rate data. I'm not going to play these videos for you again. You've seen these videos in Learning Target number 11. These are the 4 ways that we can calculate initial rate data. We can find the change in mass of volume in a reaction. We can look at the pH during an acid-base titration. We can measure changes in conductivity, and we can measure how quickly a color changes. In fact, we're going to hopefully do that in an experiment here. So here's where we're going to get to the nitty-gritty, and we're going to use those initial rates to calculate a rate law. So to find a rate law, we perform an experiment multiple times. And when we perform that experiment multiple times, in one trial, we'll control the concentration of one reactant and manipulate the concentration of the other reactant in order to see what the rate is. And then we'll repeat again in flip-flop, control the other reactant and manipulate the one that we didn't manipulate before. And we repeat this process for all of the reactants. So we're going to use that example once again of nitrogen pentoxide making nitrous oxide and oxygen. And let's pretend I perform this experiment. And this one is really simple because this one only contains one reactant, the one reactant of N2O5. And I did 2 trials. The first trial, I had 1 mole per liter of the N2O5. And the second trial, I had 2 moles per liter of N2O5. And when I doubled the concentration, lo and behold, you can see and do some mental math, I doubled the rate of reaction. And by the way, there's your rate of reaction equation, change of concentration over change in time. So I can intuitively think that this is a first order reaction because doubling the concentration will double the rate of reaction. But let me show you how to just put this mathematically. Okay, so what I'm going to do here is I'm going to make a ratio. I'm going to make a ratio of trial 2 to trial 1. And when I do that, I'm going to know that there is some sort of order of reaction that will dictate what my rate of reaction will be. And order of reaction is an exponent. So I'm going to put the concentration of the second trial here, which is 2.0. Put the concentration of the first trial here, which is 1.0. And I know it's going to have some order of reaction that is going to go to negative 0.00096 divided by negative 0.00048. And then I can do this math here, which is going to be 2 to the nth power is going to equal 2. Well, I can just eyeball this and say, all right, my order of reaction is n equals 1. So my rate law, without knowing right now what the proportionality constant is going to be K concentration of N2O5 to the first power. And you saw that earlier in this video. There's the math to prove it. All right, now we're going to find the rate constant and the units for the rate constant. So what I'm going to do here is I'm going to write out the rate law that we just discovered. We found that the rate law is going to be this proportionality constant K times the concentration of dinitrogen pentoxide, N2O5, to the first power. And if I go back, I can see that I can use any one of the trials in order to get a value for K. So what I'm going to do here is to use the rate that we found for trial 1 and the concentration for trial 1 in order to figure out what K should be. To do that, I'm going to isolate K to start, because we should always isolate our variables first. So N2O5 to the first power, all divided by both sides. And then that expression is going to give, that's to the first power, that looked like a 2. That is going to give me the rate divided by the concentration of N2O5 will give me my proportionality constant. In trial 1, and you can back up the video to prove this, the rate is 0.00048 mole per liter per second. And I'm going to spell that out here. And that's all going to be divided by the concentration of N2O5, which is going to be 1.0 moles, which is going to give me my proportionality constant. So when I solve this out, the math is incredibly simple. The proportionality constant, because it's a first order reaction, is the same as the concentration in this particular case, or the rate of reaction. And now I need to find some units for K. So there's a good reason here why I left these units in the numerator and the denominator, because I really want to see what cancels and what units are going to be left with K. What I did here is I just corrected my concentration for moles per liter. So what I can do is I can look at these units and I can see that moles cancel. I can see that liters cancel. And I'm left here with seconds in the denominator in the numerator of this fraction. So that means my units for K in this problem are 1 over seconds. And it's really important to know that the units for your proportionality constant are going to differ dependent upon your rate of reaction. If your reaction order is first order, like this case, your units for K will be 1 over seconds. But they will be different if you have a second order reaction or a zero order reaction. P.S. Yes, there's third, fourth, fifth, sixth orders of reaction. We don't get into them in this class. So that's basically giving us enough information to give us the overall rate law, which I'm going to put here. So I now know my rate law is going to be 0.00048. Concentration of N2O5 for 8, N2O5 to the first power. You don't have to put the units in the actual rate law itself, but you do need to know how we derive those units for the rate constant. Let's do a little bit more complex of an example with 2 reactants. Okie dokie, so we are now going to look at how to come up with the rate law for this particular equation when I've got 2 reactants. So what I've got going on here is I've got 2 moles of nitric oxide mixed with 1 mole of oxygen gas to make 2 moles of nitrous oxide. So you'll see that we're using nitrogen-based chemicals quite a bit, because we're going to use these later on when we are discovering the steps that are involved in particular chemical processes. So here is the data that I supposedly collected during 3 trials of this experiment where I was adding the NO plus the O2. Trial number 1 versus trial number 2, I controlled the amount of oxygen gas, and I manipulated the amount of NO gas. And then if I look at trial 1 versus trial 3, I controlled the amount of NO and I manipulated the amount of O2. So when I do this, it'll enable me to find the experimental order for NO and enable me to find the experimental order for O2. So let's see what we mean by that. We're going to first do what we did the last problem. We're going to compare trial 2 to trial 1. And in this case, I'm going to just use capital T for trial 1, not temperature, trial. And actually, I'm going to do trial 2 divided by trial 1, which is going to give me the 0.200 divided by the 0.100 to the nth power equals 0.16 to the 0.04. So this is going to be 2 to the nth equals 4. And so if I take a look here, what does my exponent have to be in order for 2 to be equal to 4 here? My order of reaction, N, is going to equal 2. So what does that mean? It means that every single time I double the concentration of my NO, I will quadruple the concentration of my product, my O2. I will quadruple the rate, excuse me. So I know my order of reaction for the first reactant. And now let's look at the second reactant here. We're going to look at controlling NO and manipulating O2. So I'm going to do trial 3 divided by trial 1. And that's going to give me 0.500. Notice I'm not even paying attention to the other reactant because I know that it's controlled and not going to change. So 0.500 divided by 0.250 to the nth power equals 0.08 divided by 0.04. And so this is going to give me an answer of 2. So I'm doubling that concentration again. To the nth power equals 2. So then my order of reaction here has to equal 1. So before I actually figure out my overall rate law, I can write what I've got already. My rate is going to be equal to that proportionality constant, concentration of NO to the second power, or second order, concentration of O2 to the first order. Let's figure out what K is going to be now. So to figure out what K is going to be, I'm going to choose any of the trials I want. I don't care which one I use. Sometimes I just do the first trial because it seems to be easier. And I'm going to find here that the rate is going to be divided by the concentration of NO2 to the second power, concentration of O2 to the first power, and plugging in those values are going to give me my proportionality constant. I'm going to fill in what I have for my data. My rate is 0.04 divided by the 0.100 to the second power and 0.250 to the first. That's going to give me K. And I'm going to grab my calculator. And if I did this correctly, I find that my K value is going to be 16. On the next slide here, I'm going to get you the units for K, but you can imagine what I would do to find my final rate law. I'll write that really fast here. My final rate law is going to be 16. 2 sig figs, or actually it's 3 sig figs because all my concentrations have 3 significant figures. Concentration of NO to the second, concentration of O2. And my overall order of reaction would equal 3. All right, last thing to do is to figure out those units for K. Let's go ahead and find out those units for K, which is our last step here. So rate is going to be moles per liter per second. So I'm going to put that in the numerator. Moles per liter per second. Divided by, and I've got 3 concentrations here. I've got moles per liter. And sometimes you may be able to visualize this, but what I'm going to do is really spell it out and realize I have 3 units of concentration, moles per liter, moles per liter. So what I'm going to do here is I'm going to figure out what units do not cancel. So I'm going to take a look and see, okay, I got 1 mole per liter on the top. I can cancel out then 1 mole per liter on the bottom. That's going to leave me 1 over seconds on the top over moles squared, liters squared. So dividing by a fraction means the same thing as multiplying by the reciprocal. So I'm going to put 1 over seconds times liters squared moles squared. And that's going to make that part go away. And I will be left with liters squared over seconds times moles squared. And that is the derived units that will be able to cancel out the units for finding the rate. If I do this, I will be left with moles per liters per second when I put them back into the rate law. So there is an example of how to get your units for K for a third order equation. Again, for every order equation, the calculations for this are going to be slightly different. This is going to be attached to an Edpuzzle that's going to ask you some questions along the way. And you're also going to see some practice work attached to your assignment on Schoology. Thanks for hanging in there with me. I will see you soon.